Have you ever heard about the intriguing blood falls? Nestled in the icy expanse of East Antarctica, this chilling spectacle is a riveting sight to behold. Blood falls, named for its blood-red hue, flows from the tongue of Taylor Glacier onto the ice-covered surface of West Lake Bonney. This geological marvel was discovered over a century ago, in the year 1911, by the Australian geologist Thomas Griffith Taylor. Taylor was the first explorer of the valley that now bears his name. Initially, the pioneers of Antarctica attributed the red color to the presence of red algae. However, further studies revealed the true cause to be iron oxides. The water that feeds blood falls is rich in iron, and when it comes in contact with atmospheric oxygen, it oxidizes and forms a striking red deposit. But what causes the eerie red color of these falls? Let's delve deeper into this mystery in the next scene. Contrary to initial beliefs, the red color is not due to red algae. Quite a plot twist, isn't it? The Crimson Cascade owes its unique hue to a fascinating process known as iron oxidation. Iron oxidation is a naturally occurring process that takes place when iron reacts with oxygen in the environment. As iron-rich hypersaline water from the Taylor Glacier emerges from small fissures and comes in contact with atmospheric oxygen, this reaction kicks into gear. The ferrous ions present in the unfrozen saltwater are oxidized, transforming into hydrous ferric oxides. These oxides are poorly soluble, which means they don't dissolve easily. Instead, they deposit themselves onto the surface of the ice, creating that striking red color that gives blood falls its name. Now let's take a moment to appreciate the age of this process. The iron-rich water originates from an ancient pocket of old seawater that got trapped under the glacier during the Miocene period. We're talking about a time approximately 5 million years ago, when the sea level was higher than it is today. Over time, as the glacier cooled down, pure ice crystallized and expelled its dissolved salts. This resulted in a process known as salt cryoconcentration, leading to the formation of brines with a salinity 2 to 3 times that of the average ocean water. This concentrated iron-rich brine is the source of the reddish outflow we see today. However, it's not just the sheer age and the iron content that make this phenomenon captivating. The Taylor Glacier stands out because it isn't frozen to the bedrock. The presence of concentrated salts from the crystallized ancient seawater beneath it probably has a role in this unique characteristic. So, to sum up, the mesmerizing red hue of blood falls is a testament to the power and beauty of natural chemical reactions, a result of iron oxidation occurring over millions of years. But where does this iron-rich water come from? Well, hold that thought as we'll dive deeper into that in our next scene. The source of this iron-rich water is a subglacial pool of unknown size. Imagine a reservoir, hidden beneath the icy expanse of Taylor Glacier, so deep and ancient that its exact dimensions remain a mystery. This subterranean pool, shrouded in Antarctic ice, is the birthplace of the iron-rich water that paints blood falls in its signature crimson hue. Now let's delve a little deeper. The water from this hidden pool doesn't exactly gush out in a steady stream. Instead, it sporadically emerges from small fissures in the ice, like secrets whispering from the glacier's icy lips. These hairline cracks in the glacier's facade serve as the conduits for this iron-rich water, allowing it to escape its subglacial prison and cascade down the face of the glacier. But why does it only emerge sporadically? Well, the answer to that lies in the unique geology of the Taylor Glacier and the pressure dynamics at play beneath the ice. The water in this subglacial pool is under immense pressure due to the weight of the overlying ice. This pressure pushes the water up through the fissures in the ice, but only when the conditions are just right. When the pressure drops, the flow of water stops, waiting for the next surge to paint another stroke on the canvas of blood falls. Now you might be wondering, why is there a pool of iron-rich water under a glacier in the first place? The answer takes us back millions of years, to a time when the sea level was higher and the Antarctic Ocean covered this region. A fjord was isolated by the advancing glacier, trapping a pocket of seawater. Over time, the iron in the bedrock below leached into this trapped seawater, creating the iron-rich pool we see today. So there you have it, a peek into the enigmatic source of blood falls' iron-rich water. But that's not all that makes this phenomenon so fascinating. What's unique about this glacier compared to others in Antarctica? Stay tuned to find out. Unlike most glaciers in Antarctica, the Taylor Glacier is not frozen to the bedrock. Quite a unique characteristic, isn't it? Now you may ask, why is this so? Well, the answer lies in the presence of salts. These salts have a fascinating origin. They are concentrated by the crystallization of the ancient seawater imprisoned below the glacier. Picture this. Millions of years ago, during the Miocene period, a fjord was isolated by the glacier as it advanced. The seawater trapped in this ancient pocket was left behind as a relic of a time when the sea level was much higher than it is today. As the temperatures dropped over the years, pure ice began to form. Now, here's the interesting part. As the ice crystallized, it expelled its dissolved salts. This process, known as salt cryoconcentration, occurred because of the heat exchange between the captive liquid seawater and the enormous ice mass of the glacier. As a result, the trapped seawater was concentrated into brines with a salinity 2 to 3 times that of average ocean water. But that's not the only way these hypersaline brines can form. Sometimes evaporation of surface lakes that are directly exposed to the extremely dry polar atmosphere in the McMurdo Dry Valleys can also lead to the formation of these brines. This process can be distinguished from the cryoconcentration process through the analysis of stable water isotopes, as long as there is no mixing between brines formed through different methods. This unique situation under the Taylor Glacier has created an environment unlike any other. The hypersaline fluid sampled from a crack in the ice was found to be oxygen-free and rich in sulfate and ferrous ion. These conditions have led to the development of a rare subglacial ecosystem teeming with life. So what's living in these extreme conditions? Let's find out in the next scene. Believe it or not, Blood Falls is teeming with life. Amid the harsh, icy conditions, a rare subglacial ecosystem thrives. This ecosystem is largely composed of autotrophic bacteria that have a unique way of sustaining themselves. They metabolize sulfate and ferric ions. Sulfate, a residue of marine conditions, and soluble divalent iron, likely released under reducing conditions from the subglacial bedrock minerals, provide the nutrients these microbes need to survive. A leading figure in the research of this unique ecosystem is geomicrobiologist Jill McCookie from the University of Tennessee. Through her studies, she discovered something truly remarkable. Water samples from Blood Falls contained at least 17 different types of microbes and almost no oxygen. This led to an intriguing question. How do these microbes survive in such oxygen-deprived conditions? Well, it turns out these microbes have a metabolic process unlike any other observed in nature. They use sulfate to respire with ferric ions and metabolize the trace levels of organic matter trapped with them. This process allows them to thrive in an environment that would be inhospitable to most other forms of life. However, there is a puzzling aspect to this ecosystem. Ferrous and sulfate ions coexist under these anoxic conditions, yet no sulfide anions are found in the system. This suggests a complex and poorly understood interaction between the sulfur and iron biochemical cycles. Scientists are still working to unravel this mystery. In fact, in December of 2014, a team led by McCookie returned to Taylor Glacier. They used a probe called Ice Mole, designed by a German collaboration, to melt into the glacier and directly sample the salty water. This ongoing research aims to deepen our understanding of this unique subglacial ecosystem and the mysteries it holds. All these elements make Blood Falls a fascinating yet little understood natural phenomenon. So, what have we learned about the mysterious Blood Falls? From the first astonishing discovery in 1911 by Australian geologist Thomas Griffith Taylor, Blood Falls has been a captivating enigma. We've explored the red hue, not caused by red algae as first thought, but by iron oxides. The source of this iron-rich water is a subglacial pool, hidden beneath about 1,300 feet of ice, its exact size still a mystery today. The unique Taylor Glacier, unlike most in Antarctica, isn't frozen to the bedrock, likely due to the presence of highly concentrated salts. And in this harsh environment, life finds a way. Remarkably, autotrophic bacteria have developed, metabolizing sulfate and ferric ions in an ecosystem unlike any other observed in nature. The interaction between sulfur and iron biochemical cycles, the coexistence of ferrous and sulfate ions under anoxic conditions, remains a complex puzzle for scientists. One thing's for sure, the mysteries of our world never cease to amaze us.